you might actually pass irrelevant context to the LLM. There's always this risk that you will actually mislead the LLM by giving it the wrong context. But having this universal relevance score helps you to limit that. Yeah, we make a lot of assumptions about what's happening in the n-dimensional vectorial space of these LLMs or neural networks. And I liked it because it was using this information theory. If you one of the criterias for splitting the classes was the mutual information. And I really loved it. And I started exploring the information, why this information thing works.
The Research Labs podcast by Sunday Pajamas.
Dr. Majid, over
Yes.
the last two conversations and some of the reading that I've been doing, and also the kind of work that I do, I feel very excited and enthusiastic about asking you a lot many questions. And it was a lot of fun to actually attend one of your sessions in University of Toronto
Yeah.
and to understand more about Edge AI and the kind of work you are doing. And today, right, I was hoping that we can maybe start with Edge AI and then go back to how the idea came to be. So if
Yes.
you had to explain Edge AI to someone, let's take two kinds of personas here. To someone who has no idea about how the AI systems work, who is like a normal user like our parents, let's say,
Mhm.
and the other one is a more sophisticated developer technical person. If they had to wrap their heads around Edge AI, could you please explain that?
Yes. I'd like to explain Edge AI and our product that we're going to launch as well. Um, but Edge AI itself comes from a very simple vision that I had about a year ago. My vision was that AI, first of all, is going to change many things. It's going to change industry. It's going to change how people work. Um, it's going to change finances. It's going to change all many aspects of people's lives. And at that time, a lot of uh, AI was done on huge GPUs, and not everyone could do it. It was just OpenAI, Google, and Microsoft that had their hands in the pot. But my vision was that going forward, it makes sense to run AI on small devices because there will be technology. I envision that especially large language models will become smaller and smaller, and on the other side, the computational capacity of devices has become better and better, even on tiny devices like a phone. That at some point, you should be able to run AI on your phone or on your laptop the same quality or better quality that you can get by going onto the large cloud. And then I thought if that's the case, it makes a lot more sense for people to do that. The first thing being preserving your privacy and data and having control over your own AI system. The second thing is, of course, uh, energy consumption. So you preserve a lot of energy by uh, putting less pressure on those giant servers. And that was our vision. That's where we started. And then we found a kind of a bottleneck in these AI systems. Um, there is a limitation to how much knowledge these language models have. They have been trained on a vast amount of knowledge, but they have not incorporated all of that knowledge. So they have extract of everything, a tiny extract of all different knowledge base. So a way of enhancing them is to use retrieval augmented generation, which you're familiar with, but to explain to like a audience who might not know what RAG is you bring in your own expert domain knowledge. And whenever these AI is trying to answer the question, you help them with giving it likely answers or likely portions of your knowledge that you think is going to help LLM to answer. And this is amazing because it helps with the problem of hallucination of LLMs. Because one of the early problems is that when the AI systems do not know the answer, they tend to generate even false answers. So this helps you to control it by somewhat, but also uh, it helps you to bring your own knowledge. And we see a lot of startups or companies that emerge uh, doing that. Like uh, there's a company that creates AI system for specialized CMOs, like um, like marketing. It's expert in crafting marketing briefs. But the people who made it, they had this their own knowledge over the years. They imparted that into that AI. They baked it into their AI system, and so on. Or you have any other kind of a specialty. That's how the special AI systems are built. Another then it makes sense to put these now on the edge devices, on tiny devices. Um, then on tiny devices, the problem of space and computation is extreme because as much as computation power you have, you want to give it to the LLM. So for the rest of it, you don't have much memory or computation left to do the retrieval augmented, to do the retrieval, basically. And that's where our product comes in. So we have redefined what similarity means uh, in terms of like semantic similarity. Because one of the big challenges is when you have a question, you want to go through your entire data, expert data, and extract what's relevant. So our way of defining relevance is kind of revolutionary. It's unique. It combines information theory for encoding, a Shannon's theory of information, which compresses the signals of the vectors, gives you a binary. And then on the binary space, you can do operations very fast and efficiently because you're just doing XOR, which is the most fundamental function that all computers do. It's like zeros and ones being XORed, which makes it very fast. And it, at the end, we recover uh, by what we call a re-rank, the relation that was lost in the binarization, quantization. We regain accuracy again by using the information theoretic score, which that was part of my PhD research. Yeah, so I stop here because I was just going on. I stop here for you to ask a question.
So, you mentioned that you found a bottleneck, that edge devices don't have the compute and the storage, and that
Yeah.
completely makes sense. But but how did you end up there? Were you experimenting with a bunch of devices, or were you simply limiting the space on a cloud instance to kind of test? How did the testing happen, and how was that one of the bottlenecks that you found internally?
Yeah, actually, the first time I encountered the bottleneck was not on edge device. It was actually on
Right,
cloud. So I
right,
was developing on one of these big cloud development uh, platforms, and
right.
they had a knowledge base offering a search engine, and I just hit it out of curiosity. I was building it for a customer, So I
right,
started just exploring it. I didn't even add much data to it. I just want to see how it works. So I came back a few days later and I saw there's a charge on our account, and it
right,
keeps going. And the claim was that it is serverless. And my understanding of serverless architecture on cloud was that you only pay as on when you use it, and
right,
the rest of time the server is not running all the time to keep
right,
your data. But this system, although its name was serverless, but it was actually charging over time. And I
right,
found that this is an issue. You cannot, once you upload these vectors into these vector databases, then there's
right,
a lot of overhead of managing these vectors. It's like
right,
everyone who's in development knows that database itself is important part of every development, and is actually one of the most difficult things that you have to manage, both in
right,
terms of resources and security and everything, like access management and all of that.
yeah, yeah,
Everything is on the shoulder of these databases. Now, vector databases are actually one step more complicated
yeah,
and more luxury databases. Um, so that's when found that if I can make it truly serverless, like
right,
when no one's using it, it's just zero cost. Absolutely, I don't need a cluster to be running on the back end. So I we created something that we call search engine instead
right,
of vector database. Well, you have a very efficient way of doing the search, and you only trigger it when you require to do the inference or you require to do this. And combine it with DynamoDB. So it was on AWS. Okay. And DynamoDB is a very good general purpose database. Uh,
right,
it has a very high throughput. The read and write is very fast, and
right,
it's truly serverless. So when you don't use it, you don't get charged for real. So
right,
we integrated our search engine into DynamoDB, and it worked very well. And then I started doing experiments.
right,
Like there was a serverless architecture on AWS, so we took that, and there was another database provider who was implemented. So we took out that database and placed our
right,
search engine, and then we started to do a lot of A/B testing.
right,
And my main focus was the accuracy.
right,
So at first, accuracy was not really there. We were struggling with to get the accurate response for the RAG. But then we did some tweaks and some optimization on the encoding side
right,
and on the scoring side. And at some point, I realized it's for me, by human judgment, it seems to be more accurate,
right,
the response that I get. But obviously, it becomes subjective if I just want to score it. Then I switched to using other LLMs like Gemini and GPT-4o to do the scoring for me. And I was really happy because the first time I did the experiment of FOSS, which is, I
right,
can share the GitHub discussion on that. Um,
right,
so FOSS is a story, goes back to 17th, 18th century uh,
right,
poem. It's a story of a scholar who knows all the science of the time and he gets bored, and so he does a pact with the devil, and so on. That's how story starts. Yeah, but it's a genius story, and it's like a public domain, so we can do
right,
everything.
right,
So I uploaded the story. So it was chunked into more than 500 chunks of information. And one of the challenges that all the rack systems have is that once you bring in your data and you separate it into small pieces, the big picture gets lost. especially if it is a coherent story. The storyline gets lost as well, especially if there's a character development on the story. That's very hard to retrieve back using the current rack systems. Um, but our method somehow, because of these information score and correlation that is formed, um, it was um, getting a 40% higher score at the end
Right.
for every
Right.
question answer compared to like Euclidean distance or cosine transform that are usually using all similarity measurements. Yeah, um, and now we are making it available. So we back in February we created the playground on our website, so anyone can go on and upload documents and start testing it. And it's not just a chatbot; it shows you every underlying pieces of. So it shows you behind the scenes what's happened, and it also gives the relevance score, which I think is really what makes it stand out, is this information theoretic score, which I don't have the complete proof, like mathematical proof for it, but it seems to be working as a universal relevance score. And people who are in the know of RAG development, they know how valuable it is to have a universal score. Um, because all these re-rankers are trying to do it, but if you have the score from the get-go, you just know where to put your thresholds, which parts of the context you want to pass to LLM, which parts you want to keep away from the LLM. Um, yeah, because let's say this scenario that you have the book, you have two completely different information in your data vector database. One of them is the story of Faust, let's say. Another one is a book on pharmaceutical chemistry. Okay. Now, if someone comes in and asks a question, and you just rely on the retrieval of vector retrieval, you might actually pass irrelevant context to the LLM. There's always this risk that you will actually mislead the LLM by giving it the wrong context. But having this universal relevance score helps you to limit that. Like you put a threshold on the mm, relevance limit, and anything below that threshold is never passes the quality test to be passed to LLM. And that also gives you leverage to create built-in security measures.
Right.
So if you
Right.
have a public-facing chatbot, um, and you have a specific context, like you are a business, you have information about your business on your website, and you only want customers to be able to talk about those topics or topics that are at least relevant to your services or products. And so you can do this easily by setting the threshold on the relevance, and it will work just universally, no matter what the topic is.
Right. And how do you internally test an idea like that one? Do you come up with multiple, like you gave two examples, one of a chemistry textbook, another of a story by Faust. So internally, do you and your team have hundreds or probably thousands of such tests going on? And I'm always, curious to understand if it feels like testing is such a tedious but yet a very important aspect of the development process.
Mhm.
So how do you think about testing, adding security guardrails and things like that,
Yeah,
especially when it comes to AGI?
I hope we had hundreds of examples, but it was limited in time. As I said, it was just in February, so we only had a few months since. But we made it available to everyone for free, and we had about 40, 50 users who came along, started using it, and gave us feedbacks. A lot of them like valuable feedbacks. So my takeaway was that even though our search is slightly better uh, in my like a exactly A/B testing, but many people have general more fundamental problems with the RAG. Yeah.
Right.
Uh,
And
s-
such as?
Such as, let's say you have a spreadsheet in your data or you have a table and you want to be able to aggregate some of the information from the table. Yeah, so RAG systems are not particularly good in those scenarios. Or you have a lot of your customer information, and like you ask a question of how many of my customers uh, did X and Y at this time period. Okay, the type of queries that you used, you you placed against a structured um, databases, they
Database, yeah.
wouldn't work in uh, rags as of today, like the normal rags that people use. Another big issue that I found was in the ingestion side of the
Right.
rag. That you could have documents in many different formats or images, and that's still one area of uh, research and development for a lot of people. So we formed some partnerships with other interesting companies and startups to cover some of these areas. For example, for OCI, like uh, bringing in images and extracting information from images, we have a nice partnership formed. And um, on the end user side, like how do you want your chatbot to look like or to interact with people? Uh, we formed a partnership to have like uh, avatars that can use the text and to communicate and so on. So there's a lot of potential for expansion. And then back to the evaluation though, there is a very good scientific research being done, especially here in University of Waterloo, that I found out recently, and they had a collaboration with Vectara, which is a leading company for RAG development, and they announced just last week, I think, just or early last week, they announced a platform where you can measure the accuracy of RAG system.
Right. Right.
Um, and we're trying to um, do some projects using that platform. It's a Python, basically Python platform that streamlines the use of creating different RAGs with different properties and
Right.
comparing the results, accuracy of the results.
Right.
And
Right.
Vectara also makes it easier because if you have Vectara API, you can just go and plug and play, change your LLM, for example, or change your
Right.
vector database and do A/B testing on rack systems.
Against, oh, right. Right.
Yeah,
So if you want, so, and do they also generate benchmarks? If you want to, let's say, take different pairs of vector databases and LLMs, so they
yeah,
could
yeah.
generate like a report. Right.
That's
Right.
the whole point. Um, there are there are certain things that are easier to benchmark, and there are things that
Right.
are more difficult to benchmark. The
Right.
easy things to benchmark is like the timing, recall accuracy, and uh, because these have like a tangible measure that you can
Right.
already measure against. But like accuracy of some responses from RAG systems,
Right.
sometimes it becomes subjective, or it's depends on your judgment. Some
Right.
RAGs are more accurate than the others, but
So,
ours is
yeah.
particularly scores high on loyalty to the original text, to the
Text.
original data provided.
Right.
And the reason for that part of the reason was that we changed the prompt and we
Right.
tell the LLM take into account the relevance score. Okay.
Right.
The
Right.
relevance, so we explained the meaning of relevance score to LLM. And
Right.
so this is a score always between 0 and 1. 0 means no relevance, 1 means exact match to the
Right.
question. Now, now that you know it, every piece of information comes with the relevance score and a tag. So
Right.
consider this in your response. And just by having
Right.
this, we kind of anchor the responses of the LLM to be more restricted to your RAG.
Right. Very interesting point you mentioned that the measurement of accuracy can actually be subjective, especially for pieces of art like Faust.
Mhm.
And when you were sharing the story of Faust, I actually have seen the example multiple times at this point that you have on your GitHub. And I think the kind of questions you ask to the LLM is, can you explain the overarching theme or meaning of the text? Like
Yeah.
questions like that. And the thing I find very fascinating, right? Do you think LLMs have a different way to look at language than we do as humans? And like,
Yes.
what do you think it says about how it understands a particular text?
Wow. This is a very big topic of research, and we just scratching the surface.
Right.
Um, Basically, these vector spaces mm,
Right.
are inside the brain of these language models or transformers. Um,
Right.
the embedding, what they call embedding, means that these phrases and words come in, they pass through these series of neurons that do addition and subtraction and multiplication, many multiplication and additions later, you end up with the
Right.
last layer of hidden neurons. It's like
Right.
we having a probe inside their brain and we bring
Right.
out the signal, which we call vectors.
Right.
And these vectors, they live in an n-dimensional space. And this
Right.
n-dimensional space is either could be like hundreds of uh, dimensions or 1,500 or 3,000 dimension.
Right.
And that space is like outer space to us. It's unknown.
Right.
We
we,
make a
we
lot of
possibly even cannot
assumptions.
visualize it.
Yeah, we make a lot of assumptions about what's happening in the n-dimensional vectorial space of these LLMs or neural networks, but we don't
Right.
know. Actually, one of the starting points for me was that uh, back in December, there was a video that went viral. There was an educational video on YouTube or something that they were talking about educational topics about these vectors and how they work. And one of the
Right.
famous things that was claimed in the video was that if you have the words of man and woman and king and queen,
Right.
and these form like vectors, and you do one minus the other, like you say, king minus man becomes the queen,
Right.
and forming a like nice triangle on the front. And right away, I thought, is this really true? Like,
Right.
like that video had like millions of views, but I went and wrote the code. I actually asked Gemini to write the code for me to do the
Right.
test, and I ran it on a Colab right away, and I saw no. I can't really say. So I created these vectors and I said
Right.
one minus the other one. So I end up with a still an n-dimensional vector. And compared to the other vector, it was not really that straightforward.
Right.
Um,
Right.
Even though that was a very popular um, assumption to make,
Right.
but it's more strange. I can just tell you that the space of vectors, the n-dimensional space, is an unknown
Right.
space. Yeah.
Right. And so, if that is the case, right, how do you think about deploying this kind of slightly mysterious systems on
Mhm.
edge devices, which, let's say, live around us in our houses? Like, can we predict how they are going to behave if we don't even understand what's going on inside of them?
Mhm, mhm, exactly. So My point is that our control systems.
Right.
Uh, let me go back up again.
Right. Right.
A
Right.
lot of um, if you look at a lot of guardrails and um, security systems that are being built for AI,
Right.
they
Right.
use AI to
Right.
monitor AI.
Right.
Basically, they ask politely to AI that you should not like do that, or make sure that these kind of words or sentences do not get on, or make sure that the bad things do not happen. But there
Right.
is a kind of a circular economy that's happening. So if you use LLMs to guard rate LLMs, there are already um, attacks that bypass that. There are some kind of attacks that makes all of them vulnerable to those attacks. So, but if we understand the vectorial space and we can map them to lower dimensions,
Right.
if I can map everything that's happening in their brain, if I can map it in a two-dimensional and I can draw circles and bond boundaries in two dimensions, and then this gives us a lot more reliable control over what's happening. Like if you, let's say you have a
Right.
chatbot and you have this conversation with the chatbot and you map all these points that you had, conversation you had with chat, then you can look it on the two-dimensional space. Okay,
Right.
so okay,
Right.
this was the greeting. The second part, I see, I can cluster them. I
Right.
have a proper metrics that
Right.
that separates them in a space and clusters them appropriately. So and then I realized, okay, this is the space of greeting. This is the space of like talking about LLM. This is the space of talking about like our own conversation. Okay, we can map the conversation, and if we use that platform or that a space to build our guardrails, it becomes a lot more like robust. It's like a mathematically robust than asking LLM, please filter yourself. Uh,
So one of the obvious questions that come up is when you are translating or mapping an n-dimensional space to a two-dimensional space, which is a binary space.
mhm.
Is there any kind of loss of information?
Yes, yes, definitely, definitely. So we are going from using float numbers, which are um, 32 bits of information, into 1 bit of information. So it's like a huge amount of loss. But uh, back to the Shannon's theory of information, that's basically Shannon's theory tells you there is one optimal way of taking signals, analog signals, and channeling them into binary, depending on how much binary you can afford to have. That's limited by your hardware memory space. But it tells you that given this limitation on the binary you have, there is one most optimal way of representing your signal into the binary. And that would still would be a loss of information, but that's a minimum loss of information. So after that, you can retrieve, if you pass that binary into a channel, at the end of channel, you should be able to retrieve certain amount of information that has been lost. And that's basically everything that's working right now in audio visual, like me and you talking, our sound gets into binary with that coding, like Shannon's coding, or images, videos get to MPEG. Like the principle of MPEG or encoding videos and audio is exactly the same. Okay. So in our way, we maximize the mutual information between the vectors in uh, real space to binary vectors, and that's it. And then once you're in binary,
It's very fascinating.
things happen really efficiently and fast and quick. And then if you want, for example, um, top five, on the other side, we bring in top 50. Okay. And then we use the information re-ranker, like information to extract out of those 50, what are the real top five? And that's what gives it like a boost in accuracy.
And I think that's really fascinating. And so now, after we make sure that yes, the data gets lost, but there is a way to make sure that it still performs the way it should perform.
Hmm.
Either is it in vector space or binary space. So now the second thing that comes up is how efficient is the binary space compared to the vector space in terms of compute, in terms of cost, in terms of efficiency when deployed in a real world system.
Yeah, yeah. It's a known. It's already known. So the process of getting calculating distances in binary is called Hamming distance, and it's been known from like 1970s, 80s, and in the vector databases, a lot of them already support binary search. Uh, if you look for binary, they already supporting this, but they don't do this information optimization. They just pick a threshold, turn this into binary, and go. That way, you really, you're compromising like, accuracy for the gain of speed. So the method, but what we are saying is that you don't need to compromise accuracy. You can have the speed and accuracy too. So that's make it unique.
and and I think this is like a good way to kind of explore how did you end up working on this.
Yeah, yeah,
How did
good.
you uncover it? Right.
So I have to go back to my PhD. So I started my
Right.
PhD at McGill in atmospheric and oceanic science in
Right.
2008.
That's so wild. Yeah.
Yeah, and my research was on forecast of rain and snow. So I was working with my supervisor, which was an amazing Professor Yao. He was one of the pioneers of cloud physics, and his book on cloud physics was basically the highest course that I ever passed. Like, I
Right.
mean, yeah. Like I studied from the let's say if you like for 17, 18 years, and the last course I took was the advanced cloud physics professor. Yeah, and then my job was to enhance the forecast of rain, and I was combining um, radar observations with numerical weather prediction models. So numerical weather prediction models like NWPs are the the most advanced, computationally heavy, and scientifically advanced methods of predicting the atmospheric conditions. And there has been many like researchers, PhDs done on it. A lot of scientists work on it. So United States has their own set of models that are being updated by the National Oceanic and Atmospheric Administration, NOAA. And in Canada, we have Environment Canada's models that are truly valuable. And then we have radar network. So there's about 80 weather radars in Canada. There's about 180 or 200 weather radars in United States, and together they create a mesh that scans the entire continent of North America, and they get updated every 5 minutes. So you get a real image. So now, if you put the image of what's rain is happening against forecast, you have 2D match. And my job was to blend the two, we to extrapolate the forecast from radars, image of radars, extrapolate it, and mix it in with NWP forecast. And I showed that this becomes more accurate in short term. So eventually, this model got implemented into the Weather Networks app because I was working as scientific programmer at the Weather Network from 2012. So by around 2014, 15, this got implemented in the app. So you had uh, a start and a stop of rain was announced on the web. So if you're close to rain, it you get notified,
Right.
and all other weather providers did that
Right.
right after.
As a result. Right.
Yes, right after that release. Anyway, so in my PhD defense, so one of the problems is to comparing forecast to observation.
Right.
If What does the accuracy of a forecast mean? So I did a deep dive into that, and I found that at the core of it, you just have a binary comparison of two binary signals. And
Right.
when you compare two binary signals, there are scores that everyone knows and uses. But in atmospheric science, it has an old history of research and scores. Uh, and uh, so I came up with this information theoretic score, which I found in a book by Satoshi Watanabe. It's called
Right.
Knowing and Guessing, which is an amazing book about information theory. So anyone who's interested in knowing more what
Right.
information theory is and how fundamental it is to the entire technology that we have, should
Right.
so read the book Knowing and Guessing by Satoshi Watanabe. And a part of this book was that the realization that um, you have two binary sets and they
Right.
have something called mutual information between them. And
Hmm.
this mutual information is interesting concept basically. It's not just how much they match, it's just how
Right.
much do they match systematically.
Right.
Means part of this matching could be random, could be by chance, but part of it cannot be explained by chance. So the part
Right.
that cannot be explained by chance alone is called mutual information. There's some information there,
Right.
and very easy way to understand is that if you have a coin and you toss the coin, and so you get head and tail. And
Right.
if you count the number of heads and tails over 1,000, if you do that 1,000 times,
Right.
it's likely that you would get equal number of zeros and ones, right?
Right.
What that means is that your coin is a normal coin. But if I
Right.
have a coin that I flip it, and after 1,000 times, I had like 80%, like 800 times head, and only
Right.
200 times tail. What does this is? This is something more is going on. Like something is
Right.
going on that is beyond explanation by the chance. Okay,
Right.
something
Right.
systematic is happening, right? And that's revealed by getting the information score, which is the uh, sigma of p log p. The p
Right.
being probability multiplied by logarithm of the probability. And if you add up for a closed system, if you go around all the probabilities and you multiply by the log of that probability, this set gives you the total information. And
Right.
then in a closed system, when you're comparing two binaries, you have a set of four possible outcomes.
Right.
These four possible outcomes gives you a space that you can still calculate the probability of each and multiply by the logarithm. And when you have two systems that are way far apart from each other, when they
Right.
don't have any mutual information, you put them together, your entropy basically does not decrease. It remains as if they are because they're two separate systems. But if these two systems have hidden relations or internal structures that are
Right.
beyond random, then when you
Right.
put them together, you see that the total information uh, decreased by certain, like entropy decreased by certain amount, and you can measure that amount, and
Right.
that's what the core of. how we measured the information theoretic score. And then in the paper I showed um, why this is better than all other scores. Like I
Right.
brought in like experiments and all mathematical formulas to show why this is performing much better than other scores in terms of it equitable,
Right.
it has resistant to nudging, it's resistant to bias. So it's a very stable score and very reliable score. And in my PhD defense, I remember when I got to that point, and
Right.
my co-supervisor, who was a lead researcher at the Environment Canada, he said,
Right.
"Okay, Majid, if this is such a good score, why not everyone is using it?" And then I was just in the mood, and I thought, he said, "Okay, I have not published it yet." Because I had not published the paper yet, and
Right.
everyone laughed, and it was like a very good, like a um, break the
Break
ice
the
cold of
ice.
the room, and everyone's happy. And then I asked why everyone laughed. I said because you were so confident that this he wanted to challenge to see if this score is really that good. But I was 100% sure that this is the score everyone should use in
Right.
doing the binary comparison. Yeah.
And in the coin toss example, if let's say we take two different sets of 500 tries of
Hmm.
tossing the coin, and if in the first set, let's say 50, there's a 50-50 split, and the second one there is a 80-20 split as you mentioned.
Hmm. Hmm.
Does it kind of mean that when you toss a coin it's not 50-50?
That individual coin is considered a random variable.
Right.
Uh, That random variable has a prior distribution, what we call prior distribution. Means that there's something going on with it that makes
Right.
it have a 80-20 distribution. Okay.
Right.
The other coin, it has a 50-50 distribution. And then when you combine them, you consider the prior as well. You take into
Right.
account that this coin from the beginning had this bias towards having 80% like head compared to,
Right.
and exactly because of that, this score is valuable because in your mostly for rain and
Right.
snow, when you look at the continental scale
Right.
radar, rain happens only in a few spaces. It's not happening
Right.
all across. So you always have only maybe 10% or 2-3% of your area covered with rain. So your forecast, if you have a forecast that's always 50-50, every place is rain, it's going to hit those 20% easily. But if you have a forecast that is also rare for it to have rain compared to no rain, and it hits, that hit becomes a lot more valuable, you see, for rare events. So there is another concept to take into account. All people who work on like machine learning, validating any kind of machine learning or forecast, they end up dealing with this problem. What if what I'm predicting is actually a very rare event? Okay, so then my model would be predicting an event that only happens 10% of the time. And they take their training and rebalance it, their techniques to avoid biasing the model. Um, but this score especially is very well designed to handle those situations and brings out the good accuracy, like the tangible accuracy in the forecast, those
Right.
situations.
And you shared that you had to invent this core system because you were trying to figure out how those two binary sets of data went in for forecasting the weather.
Yeah.
So was it like a conscious dish when you were trying to invent things like this? Do you have more control over what the outcome is going to be, or is it more of a exploratory discovery kind of a phenomenon, or
Hmm.
it's a mixture of both?
No, for me it was just kind of accident because I was a PhD student and I was doing my research on any topic that seemed interesting to me. at the time. Like it was like back in 2011, 2012, 11, I think, that I got fascinated with machine learning, even though it was not part of our curriculum at all. So I walked into one of our professor's offices and and he had a big data set of rain. Um, he just presented to us that he has one of the largest collection of data in North America about rain because we had um, we were working at radar, Marshall's radar, which was the first radar weather radar built in the whole North America. It was in Canada. It was in McGill, and they had collected all this data. And I walked to his office and I told him you should use machine learning techniques to find patterns in this uh, weather like weather data. And he said, what are you talking about? What is this machine learning?" But very early algorithms I really liked was called CART, CART, which was classification and regression trees. And I liked it because it was using this information theory. If you the one of the criterias for splitting the classes was the mutual information. And I really loved it. And I started exploring the information, why this information thing works. Mm, And, and then, yeah, I started reading books, and especially this book by Satoshi Watanabe really made me think about how I can apply it. And that's where it came from.
The reason I ask is the one thing I get very fascinated by is how not by how the process was done or how a particular project or paper was written, but how why did someone decide or choose to work on exactly that out of everything else that someone can be working on. So,
Mhm.
and when I ask that question to myself or anyone I'm talking to, nobody seemed to have like a very concrete answer for that. It's always very intuitive. I felt like it just came to me, things like that.
Yeah, yeah. So it was something that was super exciting to me,
Right,
but like it was not interesting to anyone else. It was just
right,
I
right.
would go to my friends and tell them, "Do you know what the mutual information is?" What you talking about? But to me, it was like, wow. When I learned about like Shannon's theory of information, it was like a big like light turned on in my head. So, yeah. So that's
What do you think uh, it is about that specific idea that you found to be so fascinating? That you
it
spend so
is.
much time working on it.
It is. It's not just mathematical. It's like a fundamental physics uh, rule as well. Because once Shannon had discovered this his method, he went to see von Neumann, uh, not von Neumann, Neumann. Neumann was a physicist, the very renowned physicist who helped on the quantum mechanics. He was one of the like, founders of quantum mechanics, basically. And Neumann told him, "You should call this entropy because it's relevant to entropy in physics." And maybe 100 years earlier, there was like Boltzmann who worked on the concept of entropy in quantum mechanics, and he was able to explain a lot of radiation that comes from the light or electromagnetic radiations by his formula. And after his death, like his formula for entropy became really important in physics. Uh, and there's a mathematician. He's in France. That's one of my favorites. His name Mikhail. Uh, I forgot. Mika is for. But he said among all the mathematical inventions, this entropy is unique because mathematicians found it first, and then it was discovered that it's a big deal in physics.
Right. Right.
And
Right.
it is oh no, sorry. The other way around. The other way around.
Right. Right.
Because physicists found it, like Boltzmann found its fundamental application in physics, and then mathematicians catch up with them, because usually it's the other way. Usually mathematicians find things first, phenomena, and then turns out to be found in nature. But entropy is the opposite. It's so fascinating.
Right. And do you have like 5 more minutes? I just have, I
Yes.
think, maybe two more questions here. And yeah, I would say, with respect to edge AI, how did that this entire process of research and discovery kind of feels, I think even last time you mentioned that when you start thinking about a problem, all these tools simply come to your mind naturally, and it's just a matter of applying those tools to solve the problem. And
Mhm.
so when you started thinking about edge AI, or probably you did not have the name in mind first, you had an idea first.
Yeah.
How did you realize that, okay, this research that I had done a while ago can possibly help solve this problem that we are facing in the AI space right now?
Yeah. No, it was like when you have a tool in your toolbox,
Right.
whenever you get into a new problem, you try it to see if it fits or not. Sometimes it
Right.
doesn't. Like I tried this like the same tool in predicting markets, or crypto and other stuff, like fun projects. I used it.
Right.
When I got to the vector, I didn't know that this is going to work.
Right.
I was just playing around, and I tested it, and I found that it seems to be working, and but accuracy was not there first. Then I
Right.
tweaked it, and once I found that, oh, it can be as accurate as Euclidean distance, or sometimes more accurate, then that got
Right.
me excited. But at first, I didn't know. It was just one of the tools I was playing around and testing.
Right. And then once you discover that, what is the process of taking that and then launching in the market?
Yeah, that's the process we're in it right now. Um, so the first thing you want to do is to make it just available to everyone to try and test it and get excited about it the same
Right.
way what we are. And
Right.
that's exactly what we're trying to do. Our launch would be soon. I hope we can do it by end of this month or next month. We have a stealth website that is going up, and we're gonna have our API. Of course, we still have our playground on Edge AI, but this Murche search, we call it the Murche, which is in Persian means ant, which is
Right.
tiny and mighty. Uh,
Right.
and the Murche, like ants, have a search algorithm that is one of the most efficient search algorithms that is there in the nature. If you know how the ants go around and find food, it's fascinating. Like
Right.
each ant is a
Right.
big explorer that goes and finds things, and that was
Right.
part of the naming. But
Wow.
yeah, hopefully soon we're gonna be launching it and inviting all like other researchers and developers to try and test it and uh, work with the search engine, see how it works.
Right. And actually, I would also love to, maybe when once you launch the I would love to use it and make a project or two, and really, like,
Absolutely.
try to figure out some use cases for it. Yeah.
Yeah, for sure. Absolutely. I'll let you know.
Well, I would say thank you so much for spending the time.
It was a
I,
pleasure.
I yeah, it was fun, and I hope enjoyed going back to all the research that you had
Yeah,
done.
yeah. Yes, very much. I enjoyed talking to you as well. And thank you very much for doing this.
Yeah.
And I hope people who see it would also enjoy it and get excited
Yeah.
about new research as we are.
Yeah,
Yeah,
definitely. Yeah, thank you so much.
thank you. Have a good one.